We now learn about the complex conjugate root theorem for polynomial functions. Now what we're looking into here are polynomial functions like the one we see here, in which all of the coefficients are real numbers. Now what the complex conjugate root theorem tells us is, if one of the zeros or roots of this polynomial function is a complex number, say z, then its complex conjugate must also be a root of this polynomial function. Here's what I mean. Say we have a complex number, which we'll call z, and it's equal to a plus ib. In other words, a completely generic complex number. Now, if this complex number is such that f of z is equal to 0, in other words, this complex number is a root of this polynomial function, then the complex conjugate, which we'll call z star, and is equal to a minus ib, will also be a root of this polynomial function. So we can go ahead and write then f of z star is equal to 0. Now what this actually means is that as soon as we have one complex root of a polynomial function, then we can state that its complex conjugate must also be a root. This means that complex roots of polynomial functions always come in pairs. For instance, the polynomial function, which I'll define as f of x, equals to x cubed minus x squared plus 3x plus 5. One of its roots happens to be the complex number z, which equals to 1 minus 2i. Now, thanks to the theorem we've just seen, the complex conjugate root theorem, we can go ahead and state, without even thinking, that because this complex number is a root of this polynomial function, its complex conjugate, which I'll call z star, and equals to 1 plus 2i, must also be a root of this polynomial function. And you can go ahead and check and plug in either z or z star into this polynomial function, and you'll see that it will equal to 0. Okay, so that's the complex conjugate root theorem, and if that's all you were after, you can stop watching this video now. But if you carry on watching, we're going to work through a typical exam type question in which we actually use this complex conjugate root theorem. So let's go right ahead. We're told, given 2 plus 3i is one of the zeros of f of x, which is defined as f of x equals to x cubed minus 5x squared plus 17x minus 13, find any of its remaining zeros and write it in root factored form. Okay, well let me start by moving this question to the side, like so, and now we can get started. So first of all, the question itself gives us one of the roots of this polynomial function. Indeed, we're told that 2 plus 3i is one of the zeros, in other words, one of the roots. But now, since 2 plus 3i is a complex number, indeed, we could actually go ahead and write z equals to 2 plus 3i. The complex conjugate root theorem tells us that its conjugate must also be one of the roots of this function. In other words, the complex number, which I'll call z star, and equals to 2 minus 3i, must also be one of the zeros of this polynomial function. And this means that we now have two of the roots of this cubic polynomial function. So how do we find the next one? Well, perhaps we could try finding it by trial and error, but at times that can be very tedious and definitely takes up time. No, instead we're going to use the factor theorem. Now let me start by copying the polynomial function that we were given. Remember, we have f of x, which equals to x cubed minus 5x squared plus 17x minus 13. And we've just seen that the two complex numbers, z, which equals to 2 plus 3i, and its complex conjugate z star, which equals to 2 minus 3i, are both zeros of this polynomial function. In other words, we can go ahead and state or remind ourselves that f of z equals to 0 and f of z star equals to 0. But now, if we use the factor theorem for polynomial functions, the fact that z and z star are zeros of this polynomial function tells us that x minus z and x minus z star are both factors of the polynomial function. In other words, we can rewrite our polynomial function, the one I'm boxing in gray right now, in the following way. We can go ahead and state that f of x equals to x minus z times x minus z star times another function, which we'll call q of x. And now, the trick in finding the remaining root of f of x is to figure out what this function q of x actually is. And here's the trick. If we divide both sides of this equation by x minus z times x minus z star, it gives us an expression for q of x. In other words, we can go ahead and say that f of x over x minus z times x minus z star equals to q of x. So all we actually have to do to find q of x is to divide f of x by x minus z times x minus z star, where z and z star are the two roots that we found at the beginning. So let's go ahead and do that. The first thing I'll do is actually figure out what this product on the denominator is equal to. In other words, we have x minus z times x minus z star. That's equal to x minus z, so z is 2 plus 3i, notice that I'm writing it in parentheses, times x minus z star, which is 2 minus 3i. Again, I write that complex number in parentheses. Now we distribute, and in doing so, we find that this equals to x squared minus 4x plus 13. And by all means, go ahead and press pause and check that for yourself. That should be the answer. So, going back to the expression for q of x, we need to divide f of x by this quadratic function. And to do that, we use long division of polynomials. So let's go ahead. We're dividing f of x, which remember was x cubed minus 5x squared plus 17x minus 13, by x minus z times x minus z star, which led to the quadratic we found a minute ago. In other words, we're dividing f of x by x squared minus 4x plus 13. Now to do this long division, we need to find what we'd have to multiply x squared by for it to equal to x cubed. And it doesn't take us too long to see that that would be x, so I write x at the top. And I now multiply this entire quadratic by x and write the result directly beneath f of x that we have here. So let's go ahead. We have x times x squared, which is x cubed. So I have x cubed here, minus x times 4x, which is 4x squared, which I write directly beneath the 5x squared there, plus x times 13, so that's 13x, which I write right here. And I now subtract this entire result from f of x, like so. So I have x cubed minus x cubed, so that's 0, negative 5x squared minus negative 4x squared, so that's negative x squared, and 17x minus 13x, which leads to 4x, and finally, I carry down this negative 13, so I have negative 13 at the bottom here. Now that that's done, I repeat the process and figure out what I would have to multiply x squared by to get to negative x squared. And it doesn't take us too long to see that we'd have to multiply x squared by negative 1 for it to equal to negative x squared, so we write minus 1 at the top here. We now multiply this entire quadratic by negative 1 and write the result directly beneath the quadratic that we have here. So let's see, we have negative 1 times x squared, that's negative x squared, minus negative 1 times 4x, so that's minus negative 4x, in other words, that's plus 4x, plus negative 1 times 13, so that's minus 13. And now subtracting this result from the row above it, we quickly see that this equals to 0. And this 0 tells us that when we divide f of x by x minus z times x minus z star, the remainder is 0, which confirms that these are both factors of f of x. Most importantly though, at the top of this long division we have our function. That's q of x, the quotient function. And going back to the result that I'm currently boxing in green, we can now state that f of x is equal to x minus z times x minus z star times x minus 1. Or going further and replacing z and z star by their respective values, we can go ahead and write this as f of x equals to x minus, in parentheses, 2 plus 3i times x minus, in parentheses, 2 minus 3i times x minus 1. And at this stage, we've written this polynomial function in its root factored form. And we've stated the values of two of its roots. Those were 2 plus 3i and 2 minus 3i. But we can see quite clearly from this root factored form that if x equals to 1, this last factor will equal to 0, and therefore f of x will equal to 0, which tells us the remaining root. The remaining root is therefore x equals to 1, or since we're working within complex numbers, we can say z equals to 1. And there we have it. Those are the three roots of this cubic polynomial function, and that's the end of a typical example in which we make use of the complex conjugate root theorem. And that's it for this tutorial.